Okay, so today we're going to be going over some introduction into sanitary and environmental engineering today. So as we go into it, we're going to just start off with some definitions as we're going to define. We're going to define three definitions: wastewater, a system, drinkable water, and pathogens. All right. So as we define these, wastewater system is a system of contaminants after human use. So this is an example of this is anything that comes out of the human body. So bacteria or even just items in a toilet. Awesome. So the next one is drinkable water. So drinkable water is safe water that can be used for humans to drink. Our next definition we're just going to define today is called pathogens. Now, what pathogens are, they're a mixture of some bacteria that can be harmful to humans. So bacteria that can be harmful. This can be ingested or just ingested with food or even water as well too. But for now, we're just going to give it to water. So bacteria that can be harmful. All right. So as we go into this introduction, we're going to go over different forms of water. So we have our first form. I'm going to put this in actually spread. So our first form is fresh water, which is an example of freshwater lakes, rivers, etc. Right, so it's fresh water. So it's not safe drinking water because it's just a fresh water in a body of water. Our second one is drinkable water, which we mentioned above is safe water that can be used to drink. We have our third one, wastewater, which we defined as human waste in whether it be that we expose from our body, right, usually in the bathroom. And our fourth one is reusable water. So the reusable water is water recharged back into groundwater, back into groundwater that used to go back to a lake. So that groundwater that goes back to lakes, for example. So for reusable water, right, it's water that's been cleaned and recharged that's safe to go back into a fresh body of water. Like for example, let's say I use the bathroom, brush my teeth, I spit the water out of my mouth into the sink. As it goes to the piping system, that water or whatever I street out the water I used to brush my teeth goes back into the freshwater system of, for example, Lake Ontario. All right, so as we move on, we're going to find two types of systems. So wastewater system, treatment system. So this treats what we have is wastewater over here. So part of our wastewater system consists of, first it goes from one of our houses. So for our combined system of our house, it goes into first a screening. So what the screening does, it screens items, right? Screens what's in the actual wastewater. So screening wastewater, that part. So it screens the wastewater. Two, it goes into a grit. So grit vortex. So grit vortex, right? It takes out like stones, right? Anything that's inside the area. So stones, leaves, it takes this out, etc. So it takes out. Or it even just separates it. Our next one that we can define as is our primary clarifier. So what this does, this dissolves items that need to be cleaned. So for example, let's say we have a cup of coffee. So this is my cup of coffee, and we're going to put this as my coffee, right? Coffee here. I know I spelled that wrong, but we're just going to put this as coffee. So coffee. And this blue stuff that's in the coffee is going to be, let's just say for now, it's our sugar. So it cleans any dissolved ions. So instead of drinking this coffee, and as I drink the coffee, I add sugar into the coffee. So what the primary clarifier does in this situation, it cleans / or dissolves. So better word, dissolves the sugar in liquid. So this dissolves, like when I'm drinking the coffee or I'm drinking sugared water or a sugar drink. This clarifier will clarify any sugars or any other chemicals that can't be really used in a fresh body of water system. So it cleans up the sugar. Our next one is our bioreactor. Right? This is one where so as the sugar dissolves, or we make sure the sugar dissolves in the water, our bioreactor, we add microorganisms. We add microorganisms to eat the dissolved materials. So if we use our example above with the coffee and the sugar, these dissolved materials, in this case, for example, will be the sugar that we use. So this our microorganism will eat the sugar. So after we do this, we have our, let me actually write it a little bit better, our second clarifier, which clarifies again. And then our last one, well, two, we have our disc filter. So it's a filter, right? It's self-explanatory, so it filters out the water. Filters water. And our last one, before it goes to lake, right? This is our last step, right? We want our wastewater up here to go into our fresh water. So it goes UV disinfection, sorry. So it gets rid of the microorganisms, right? So even though the microorganisms can be good to eat, the dissolved materials, we don't want this to go into our lake, right? We don't want it because it's not good for our ecosystem. So as we move on, we're going to go into our next one. So the difference between this one starts from wastewater. It goes to lake, freshwater. That's our goal. The next one is we have drinking water. So our goal is to get our drinking water treatment system. That's our end goal. All right. So the first one is going to be, ready, our ozone disinfection. Right. So what this is from? So this first one actually, I'm from lake water. Right. So lake water to drinking water. We have ozone disinfection, which what it does, it destroys like diseases. So disease prone microorganisms. So any bacteria or microorganisms that can cause diseases in the water, that's what it does. It uses to kill them or reduces the chances of them. Our second one is a collagen. So with a collagen, where we have very fine particles adhering together to form larger particles. So the particles are removed. Or this is what I like to call a filter. So it's a filter in the water. So it's another filter. Third part is the acetylene. So how they actually filter, they spin it. So it spins. right? Settling is the next one. So these particles are further removed, so removed from the last one, are settled. So this means they're settled out of the water. So now one was cleaning it, now this is settling out of the water. Our fourth one is our bioactive filter. And what this does, the water is filtered again. So filtered to remove even smaller particles. The fifth one is going to be a chlorine disinfection. What this does, right, with the name implied, it is adding chlorine. So adding, I'll put the chemical compound, Cl, as a disinfectant. So as a secondary disinfectant. This provides extra protection for potentially harmful microorganisms. So extra protection, this is what it does. From microorganisms that may have slipped through. Right? Our sixth one is adding fluoride to it. So this helps tooth decay. So it helps, like when we drink water, if you didn't know, fluoride is a little bit in each when we drink our tap, right? When we drink water, so it helps tooth decay. Right? So it helps clean up our teeth. Right? So when administered in low levels though, so low levels. So making sure we clarify we're not adding a lot of fluoride in, but with low levels, it helps our tooth decay. 7 is a clear wall. What this does, it's stored in deep underground tanks. Deep tanks, underground. What this does, helps it through and helps our distribution system. So it helps it go underground and gets through our system what we need. Next one is corrosion control. So what this does, so corrosion control, this helps us so the water does not corrode our pipes, as much as it does. Even though water is a little bit acidic, right? And we help to not lead to lead or copper in our pipes. So what it does is lead corrosion. There's less corrosion in our pipes. As the less corrosion happens, less free from poisoning from copper or lead. Right? 9 is our last step in the system before we go into it. And we have chloramine protection. What this does, this helps this disinfectant remain protected. So disinfectant remain as a protection system when the water is being distributed throughout the thing. Throughout our system, whether it be water, and through our taps as well too, right? So make sure that the disinfectant stays. And then our final one, we end up with drinkable water. So this is where we end up with fresh water to drinkable water. So the difference in these two systems, right? One's waste, one's treated, where we go in, where the difference, what the water treatment system, so I'm going to label these as system 2 and system 1, just so we're all on the same page. So system 2, system 1. So system 2 has less solids present, right? Versus our wastewater, we have a lot of solids present because it's a waste, right? It also has almost none organic matter, right? Because it's mostly water. So we have microorganisms, of course, but not really any solid organic matter present. But in our system number 2, to be able to drink it, this is very important. Right? Although this has more pathogens, it must be 100% clear once it leaves the system, and clear at the end. So once it leaves, it has to be 100% clear because it's safe to drink, right? We can't have people getting sick with our system. We have to make sure that our water is nice and clean. All right. So that's the difference between two, where system 1 goes from waste to fresh, and the other one goes from fresh to drinkable. Fresh, I'm going to put fresh/reusable. Right? We want our water to be reusable. All right. So as we go down into our next couple of slides, we won't start with our chapters, just chapter 1, which is just a basic introduction into wastewater, the system of just wastewaters. All right, and wastewater treatment as well too. All right. So wastewater is divided in 3 parts: physical, chemical, or biocontaminants. That's bad for us, or hazardous. That can be discharged, and that can be discharged into environment. Can go into our environment. The reason we treat this is because we want to protect ourselves. So protection from our safe environment. So protection of water, the environment, so I'm putting an arrow here, as well as we have to meet legal. So legal and laws. We have to meet our legal and laws because this is important for safety, but also meeting the right laws. So we have to make sure that this is as safe as possible, right? So some sources that we can add to this, right? Sources of these containment of water consist of domestic and industrial. So divided into 2 parts. I'm going to put one is domestic and this is industrial. So industrial is pretty self-explanatory. It's any factory waste that's reduced or to make it a product. Well, domestic is a little bit more local, which is into residential. Our first point over here. Commercial, second point is a commercial use, and stormwater. So water from storms or inflation flow. So these are kind of categorized, our residential areas categorized in black and gray water. So gray, actually black, I'm going to write in black. So keep the color same. So black water is toilet waste. And only toilet waste. Put only. While gray, let's see if I actually have the color gray. Oh, I do. So the color gray is waste consists of sinks, showers, etc. That's basically not in a toilet or not toilet waste. Or not considered that. So it's not considered toilet waste. We have to note that when considering waste and the industrial waste, that the velocity, so V would equal velocity of the system should be at least 0.6 meters per second. Right? Ideally, we want it to be 0.6 meters per second, but it could be as well 0.6 to 0.24. But we're trying to get to this point that I just started. As an addition, manholes are located near each other at 90 to 150 meters. So when we're driving down residential roads, or even just roads that exclude the highway, we notice that there are manholes or even manholes that have our sewer system every 90 or every 150, and they're on the same side of the road accordingly as we go through our piping system. So as we go down to our next point, so we talked about the flow rate, that what it needs to be, right? So when we have our flow rates, right? Our flow rates, at some trends that we find, it's lower during the weekend. During the weekend, right? This is due to whatever reason that may occur, but it's higher midweek. This is due to when the collection of wastewater, right? Storms mostly happen during the week, and when we have it, it's higher during the midweek. And it's also the average flow rate. So flow rate we're going to define as Q, right? So average flow rate is usually higher, right? Higher during wetter periods. So let's say rainy season, we have our average Q a little bit higher during wet seasons throughout the year. So as we go down, we're going to find more flow rates as well too. So let's actually keep it. I think we keep it here. Yeah, we're going to keep this here, right? So our flow rates, we have Q average. So what this is the average flow rate, which is defined by Q, over 24 hours, right? Our Q peak, so this is our peak hourly flow rate. So our peak hourly flow rate, so by hourly, so hourly flow rate is based on peak hourly flow in the 24 hours. So 24-hour period. We also have our Q min. This is our minimum flow rate. This is also by hourly. And this is the same thing as the top, but min Q and 24-hour period. So as we do this, I'm just going to turn it off, make sure nothing pops as a notification, right? As we go up. So I'm going to show a little graph. So I'm going to make a little graph here, right, just to show. So with our graph, we have y, x direction, x, y. We can define our x value as time, because time is always continuous. We define our y as our flow rate, but with the value of q. All right, so flow rate on y, time on x. So as we do with these two, right, we have three things. So we have, in red, three levels. We have q peak, q average, and q min. So this is our flow rates. If we use a graph just to distinguish, let's say, it goes up, down, and back to center. Let's just say that. We are design for our flow rate average, right? That's how we designed our system. This is due to cost plus time, right? We want to make sure, as engineers, we want to make sure it's nice and efficient. But we test for peak. Just in case we have a flood or a rainy season, we want to make sure our system can handle our peaking factor. So that's going to be our next thing, actually. So as we scroll down, our peak flow factor. So as we go to our peak flow factor, the equation that we can define it as, when we define that, so it equals PF, so peak factor, so write that down here, peak factor is equal to max flow divided by average flow, or Q max divided by Q average. So as we do this, right, as we do our factor, we have to consider where different cities, different areas of when we live, right? So we can calculate so where each kind of peaking factor will change depending on the area you live in, right? So depending on the area you live in, it can go higher, it can go lower. But we can use our empirical formula, PF equals 14 times P, which is our peak, to the power of -1/6. So we can use this as well too. All right, so as we explain our peak factor, we're gonna keep going for an example. So we have a countryside or even just a small town with a population of 25,000 people. They plan to build a residential wastewater flow rate to estimate about 3 million liters per day, right? As something else is coming in, new factories coming in, and they're going to be contributing a flow of whatever is coming out of that factory of 2,000 meters cubed per day. So our goal is to find peak flow, right, in meters cubed per day. So our units are very important. So our solution to this, when we're going to find this out, is we're going to change this color to pink. PF, remember PF equals, we use 14 times P to the power of -1/6. Using BEDMAS rules, we're going to add this up to 14. So P, actually, I forgot to mention, I should mention this over here, the population. I should have added that in, I apologize. So P is our population, so it's 14 times 25,000 to the power of -1/6. So if we do this quick math, we're going to do 25,000 to the power of -1 divided by 6, right? And then times this by 14. We get an answer of 2.589. So this is our peak factor, right? So it's going to be unitless. So now we're going to find out our daily peak of wastewater flow. So wastewater flow. So as we find this, we're going to find out, remember our Q average of our flow is going to go down here, is going to be 3 million, right? And this is good. We're going to times this with our peak factor, remember? So with our peak factor, we're going to multiply this by 2.589. So as we equal, right, and so it would be 3,000,000 times 2.589. This equals our 7,6,7,0,0. So what if we do with our units, because remember we're doing liters, this is in liters per day. So when we convert the units, right, we'll make sure we have a unit conversion. So what do we do for liters per day? So what we can do is use a calculator online as well. So if we do liters to meters cube, the conversion rate is 1 liter equals 0.001 cubic meter. So as we use this, we can times this by 0.001, and our answer, what we can get is, times 0.001, is going to be 7,767. Remember, we have a new unit, meters cubed per day. Awesome. So now we convert our units, make sure it makes sense. So now, as we found the daily peak, we're going to also find, so this was daily, I forgot to mention, residential. So our population. But now we're going to add on to our daily peak overall. So this is with the factory involved. So we're going to take our 77,000, right? And we're going to plus our flow, which is going to be, right, 2,000. So the flow, peak flow, right? So peak Q max. So I'm going to write that here. Q max, which is 2,000, right? We have 2,000 meters cubed per day. And since both units are meters cubed per day, there's no conversions. And this can be added up to 7767 plus 2,000, 9767 meters cubed per day. So that's an example we can do here as well too. Awesome. So as we scroll down, right? We're going to work characteristics of this wastewater, right? So we mentioned above that domestic wastewater water consists of 99.9% water and 0.1% solid. Even though it's a small amount, we still have to consider that the amount of solids, right, in our water, right, even with one person, right, including millions of people. As we mentioned before, it characterizes physical, chemical, and biological parameters. So remember, as we talked about before, characterize those three things, right? And we also have chemical characteristics. So we're going to divide this up into chemical characteristics. So it divides into two. We have organic. We also have, put this over here, inorganic. So organic concludes, for example, organic compound, so TOC, right? We could also get BOD, which is biological oxygen demand, and as well as chemical oxygen demand, right? So this is typically consists on proteins and carbohydrates. So I spelled proteins wrong. Let me just fix that. But the consistent of, we have proteins and our organic matter, right? And carbohydrates. While our inorganic consists of pH level, so acidic, right? Metals, nutrients, and this consists of anything that is, right, acidic, like sulfate as well too, acidic and non-acidic, etc. here. So one is protein carbohydrates, the other one's kind of acidic and like different types of metals in our periodic table, right? So our physical parameters, add this over here, consists of solids, dissolved solids, temperature, or color, right? Color of the water. This one, biological, consists of pathogens and viruses, right? Anything bio. So pathogens plus viruses. Awesome. So as we just defined all three. So as we keep going down, right, we can characterize different more stuff and keep going through different things, the type of characteristics, right? Total suspended solids, our bio-oxygen demand, and stuff like that. So for now, we're going to leave it at that. So as we talked about today, so if we scroll up, a little bit of review, we defined different types of forms of water. We defined two different systems, our waste treatment system, as well as our drinkable water treatment system, right? Differences include, right, different able to drink, and differences from waste to reusable, from reusable fresh water to drinking water. We characterized some domestic sources of wastewater. We'll be focusing on flow rates of systems, as well as what we're designing them for, peak factor of our flow rates, as well as characteristics in water that we might need to look out for. So I hope you guys have a great day.